All right. So in the last class, I defined the determinant of an n by n matrix in terms of permutations. Right? It's a different definition than probably what you've seen previously, but essentially it boils down to the same. It gives you the same thing as you would get using the cofactor of a matrix. All right. But in any case, I mean, this particular expression for the determinant as well as the cofactor approach, uh, it does not yield a computationally efficient way of finding the determinant. Right? In the end, the computation scales as n factorial, which is even faster than exponential in n. Right. So is there a way of computing the determinant of a matrix efficiently, hopefully in time that is polynomial in it, using number of operations that grows maybe as a small polynomial, as maybe as n cube or n to the power 4. Right. So that's the agenda of the first part of this class. And the main, the basic idea behind designing an effective or efficient algorithm again goes back to row reduction. Right. So let's see what happens to the determinant when we perform row reduction. After all, you have a given matrix A. Using row reduction, you can bring it down to, let's say, the identity matrix, or in general a diagonal matrix. Right? We know how to compute the determinant of a diagonal matrix. What is the determinant of a diagonal matrix? It's just a product of the diagonal entries. All right, so that's something that we can very easily compute, no difficulty. So what happens every time I do a row reduction operation? Every time I perform a row operation. As we know, there are three types of row operations. One is where you take linear combinations of rows. The other where you scale a given row. And the third is you perform row exchange. All right. And as it turns out, you can characterize exactly what happens to the determinant for every row operation. And that's easy to characterize. I will not completely prove this. It's not very difficult to do. But essentially, this is what happens. So suppose I have a matrix A and I perform a type 1 operation. So in a type 1 operation, I take a row, the ith row, I subtract some alpha times the jth row from this, and replace the ith row with this particular quantity. All right. Then, in fact, what happens is that the determinant doesn't change. Determinant of A prime is equal to determinant of A. And the reason why this is true, just to give you some intuition, I won't give a full proof, but it's not hard to fill in the details. But basically, you take, again, let's try to think about it in terms of the cofactor the cofactor kind approach. So essentially, what are we doing? We're taking the ith row, and we have the ith row minus alpha times the jth row. Right? So firstly, if you think about it carefully, if you try to expand the determinant in terms of the ith row of the new matrix, then it essentially becomes the determinant of A minus alpha times the determinant of another matrix. Right? So the main idea is the following. So the first kind of operation is Ri prime is the ith row minus alpha times Rj. All right. Now, if you expand about Ri, right? Let's assume that you're taking the first row and you're subtracting. So you have a matrix and I is equal to 1. So this the first row of the new matrix A prime is basically the first row of the old matrix minus alpha times alpha times maybe the second row of the original matrix. All right. Now if I expand the determinant, right? The determinant looks like this term times some cofactor matrix minus the second term times some other cofactor matrix, and so on. Each of these cofactor matrices in A and A prime are the same because I have not touched any of the other rows except the first row. Alright. So since the other matrices are essentially untouched, the determinant is in fact, it's a linear function of the first row. Right. So the determinant of A prime is equal to, so essentially I can write the determinant of A prime as maybe the determinant of A minus alpha times the determinant of another matrix where all of the rows, the second, third, fourth, and so on, all the remaining rows are the same as A except for the first row. But what is the first row? It's equal to the second row itself, right? So this, right? So this is A itself, determinant of A, minus alpha times the determinant of some matrix A double prime, where this A double prime has the first row equal to the second row and the other rows are whatever, it's the same as the original matrix A. What would be the determinant of this matrix? It is 0 because it's essentially the same row repeated, right? It's not a full rank matrix, correct? So the determinant of A prime is just equal to the determinant of A. It remains unchanged, right? So that's a nice property. Okay, so type 1 operation, we know what happens, right? Now let's look at a type 2 operation wherein you just scale a row by a constant. What happens to the determinant? It is just alpha times the determinant of A, right? In fact, so the main idea that we use is, even if you go back to this expression for the determinant, right, you can see, you can convince yourself that the determinant is a linear function. If you keep all of the other rows constant and you look at it as a function of just the first row, then it's a linear function of the first row, right? And that is where we get all of these, the first property as well as the second property, right? And it's the same if you want to think about it in terms of the cofactor approach, then you essentially expand about the ith row. If every element of the ith row is multiplied by alpha, then the determinant itself is also multiplied by alpha, right? Okay, so type 1 operation, determinant remains unchanged. Type 2 operation, determinant is just scaled by a factor alpha. Okay. The third operation is just you exchange two rows. What happens to the determinant? In fact, any row swap or any column exchange, the determinant just switches the sign. So the determinant of A prime is negative of the determinant of A. And why is this true? If you think about it in terms of the permutations, then effectively you are just swapping two rows, which amounts to a pairwise exchange of two rows. And you know that you're essentially adding another pairwise exchange. So the sign, if the sign was +1, it just becomes -1 for that particular permutation. All right. Any questions so far? Okay. So type 1 determinant remains unchanged. Type 2 just scaled by a factor alpha, and type 3 sign change. Nothing else. Okay. Now we have all of the ingredients that we want to be able to compute the determinant. How so? So let's take our matrix. We have an n by n matrix. Let me first compute, so I'll compute the row reduced echelon form, but at the same time I'll keep track of what all operations I did in order to get to this row reduced echelon form. Okay, so I start with the matrix A, I perform some row operation to get matrix A1, I perform the next row operation to get matrix A2, and so on. Maybe the first operation that I did was, maybe a type 2 operation where I scaled the first row by some factor. Maybe the second row operation that I performed was a type 1 operation where I subtracted from the second row, I subtracted some constant times the first row. The third operation, maybe I had to do a row exchange. So it's a type 3 operation, and so on. Okay, so I make a sequence of such row operations, and I keep track of every time what factor I scaled the row by, and I also keep track of how many times I exchanged rows. Okay. All right, and using this particular approach, I finally end up with the row reduced echelon form. So this is a matrix A prime. Now, what is the determinant of A prime going to be equal to? I mean, forget about all of those the operations that I did. What form does A prime take? Okay, so I'm assuming that when I do compute the row reduced echelon form, correct. So identity element, in fact, it's a diagonal matrix. I'll try to bring it down to a diagonal matrix. In fact, that's not also required. It's enough if I just end up with an upper triangular matrix. All right. But in any case, what possible values can determinant of A prime take? 1 or 0. So if it's a full rank matrix, the determinant is going to be equal to 1 because all of the diagonal entries are going to be non-zero. It's full rank. And if it is not full rank, then I'll end up with a diagonal matrix where some of the entries are 0 and therefore the determinant is equal to 0. So the only possible values that determinant of A prime can take is 0 if A is not full rank, and it's going to be equal to 1 otherwise. Okay, great. So now, so this is from one perspective. I know what the end result is going to be, what the determinant is going to be. Now I performed a sequence of operations to get to determinant to A prime from A. So I started with A and then got to A1, which was maybe a type 2 operation. What happened? Effectively, the determinant of A1 is going to be alpha 1 times the determinant of A. Correct? Because I did a type 2 operation where I scaled the first row by some constant alpha. Then I performed another type 1 operation and the determinant was remained unchanged. So determinant of A2 is equal to determinant of A1, which is alpha 1 times the determinant of A. Then maybe I did a type 3 operation. So determinant of A3 is the negative of determinant of A2. So that is just going to be minus 1 times alpha 1 times the determinant of A. Right? You keep repeating this. You do this sequentially. So you'll maybe have some more type 2 operations where I'll multiply the row by some constant number, and I have to perform certain number of row exchanges where I have to multiply by minus 1, and so on. All right, that's it. So So basically this is going to be equal to minus 1. How many times does minus 1, do you multiply by minus 1? It's equal to the number of row exchanges that you did during your row reduction process. So it's minus 1 to the power of the number of row exchanges that I had to do times all of the factors that I had to scale by, right? So this is some alpha 1 times alpha 2. Maybe I had to do some m rescalings. So I did m type 2 operations during my row reduction process times the determinant of A. All right, great. So now if the determinant of A prime is equal to 0, that is, it's not full rank, then I don't need to do anything. I know that the determinant of A is equal to 0. If the determinant of A prime is equal to 1, then the left hand side is equal to 1, and I know all of these quantities over here. So it's very easy to compute the determinant of A, right? It is just 1 divided by this whole thing. It is minus 1 to the power of number of row exchanges times alpha 1, alpha 2, and so on up to alpha n. Right? So now I have a simple algorithm to compute the determinant. What is the computational complexity? How many row operations do I have to do to bring a matrix down to the right? So I just have to do order n square operations, order n square row operations, or the number of arithmetic operations that I'll require would be order n cube. So from n factorial, right, n times n factorial complexity, I now have a very simple algorithm that I can just do in order n cube complexity. So in fact, finding the determinant is as complex as solving a system of linear equations, because this is the same complexity. In the end, in each case, all I have to do is bring the matrix down to its row reduced echelon form. Why? Okay, so that's how you define the determinant. This is an algorithm to find the determinant, right? And it has its own values, this particular approach. There are, as we'll see in just a moment, there are different interpretations of the determinant of a matrix. So depending on what angle you view it through, the determinant can have different physical interpretations, right? Again, I will not discuss all of the different mathematical and physical interpretations of this, but I'll try to give some geometric interpretations of what the determinant is. All right? But if you want to compute the determinant of a matrix, then this is how you should be going about doing it, right? Not using the cofactor approach. The cofactor approach is helpful because there's one value to this particular expression for the determinant of a matrix because it's a closed form expression, right? I know exactly how it behaves in terms of each and every entry of the matrix, which I don't have if I try to look at it through the row reduced echelon form approach. That gives me an efficient algorithm, but it's difficult for me to get intuition as to how the determinant behaves as a function of its entries. Correct. So this is effectively the same. This gives you the same as your cofactor method, right? So you treat this as the definition, right? How you define the determinant. The Cofactor approach gives you a recursive but inefficient algorithm to compute the determinant. And this row reduced echelon form approach or row reduction approach gives you a way of efficiently computing the determinant of a matrix. Now in practice, there are other ways. For instance, the determinant of a matrix is simply a product of the eigenvalues, right? Sometimes, if for certain special classes of matrices, it is easier to compute the eigenvalues than use the row reduction kind of method. In those cases, you just try to diagonalize the matrix or find the eigenvalues and then just take the product of the eigenvalues. Sometimes that is going to be faster, but for a general matrix, this is one of the most efficient approaches. But at the same time, this does not give you intuition as to how it behaves as a function of the entries of A. Because after all, this determinant depends on these scaling factors alpha 1, alpha 2, alpha m, which you don't know how it behaves as a function of the entries. Any other questions? Sure. So these scaling factors are not going to be the norms of the column vectors at all. They're going to be something totally different. So that is why it is difficult to interpret these constants in terms of the rows or the columns. They could be some very complicated functions. So this particular approach does not give you too much intuition as to the behavior of the determinant, but it's a very simple way of computing it. So you can just write a program, even for a very large matrix, you can compute it very quickly. Whereas you cannot do that using the brute force approach or using the cofactor approach. The cofactor approach, yeah, maybe for a 3 by 3 matrix or a 4 by 4 matrix, you can compute it easily by hand or even by writing a program. But let's say I gave you a 500 by 500 matrix, you can't, right? But in fact, using this approach, you can find it quite efficient. Just as a simple exercise to find out what we've seen so far, let's try to compute the determinant of this simple 3 by 3 matrix. If you use the cofactor approach, what would the determinant be equal to? Plus 2, right? So this would be equal to plus 2. The easy approach is to expand about the second row. So it's minus 1 times 1 into 2 minus 2 into 2. So that's just equal to minus 1 times 2 minus 4, which is equal to plus 2, right? Now let's use the approach that the row reduction approach. So I have 1, 2, 3, right? Let me just write down the full matrix: 0, 0, 1, 2, 2, 1. So on this, let me first perform a row swap operation. Let me just exchange the second and the third rows before I do anything else. So this is a type 3 operation on the second and third rows. I'm sorry, this is a type 3 operation. So I get 1, 2, 3, 2, 2, 1, 0, 0, 1. Okay. Next, let me perform a type 1 operation where I subtract the second row. From the second row, I subtract the first row, right? So this is R2 prime is going to be equal to R2 minus R1. What do I get? 1, 2, 3, 1, 0, minus 2, and 0, 0, I'm sorry, I should subtract minus 2 times the first row. Right? So this is going to be 0. The second row minus 2 times the first row is going to be 0, and 2 minus 4 is minus 2, and 1 minus 6 is minus 5. I have 0, 0. All right. Now I want to normalize the second row. So I will perform a type 2 operation where I'll scale by minus 2. So I get 1, 2, 3, 0, 1, 5 by 2, 0, 0, 1. I'm sorry? Yeah, scale by minus. That's correct. Right? Basically, I divided the second row by minus 2, or in other words, multiplied it by minus half. Okay, good. I don't need to proceed any further because I have an upper triangular matrix, and the determinant of any upper triangular or lower triangular matrix is just a product of the diagonal entries, right? And all of the diagonal entries are 1. The determinant of this matrix is equal to 1. This is not RREF. So I said RREF because it's easier to think about what the determinant is, but I don't need to go that far. I just have to bring it down to an upper triangular matrix. I just need to row reduce it to an upper triangular matrix with all the diagonal entries being equal to 1. That is enough.
Okay. Stopping here gives you some complexity reduction computation.
The order of the computational complexity doesn't change, but definitely there's a reduction in computational complexity. In fact, half the complexity is reduced. Right? Okay, now let's keep track of what we did. Remember that the determinant of A is 1 divided by the number of swaps that I had to do. How many swaps did I have to do? 1. So it is minus 1 times all of the scaling factors that I had. I had only one scaling factor in this particular example, which was minus half. So this is just equal to 2. Right? Now, for a 3 by 3 matrix, this seems like overkill because if you use the cofactor approach, then you could just calculate it very quickly. But now I have to perform these many row reduction operations. So for a small matrix, this is not particularly helpful. The cofactor approach is far easier to compute for a 2 by 2 or a 3 by 3, maybe even a 4 by 4 matrix. But as soon as you go to larger matrices and maybe you want to write a program to do it, then the row reduction approach is really beneficial. Right? Okay. Any questions? All right. So this was what the determinant. So we've seen what the determinant is and how do you compute the determinant efficiently. So now let's change perspectives and look at eigenvalues and eigenvectors. Right. So recall that real number lambda is an eigenvalue of an n by n matrix if you can find a vector, a non-zero vector, such that a times x is equal to lambda times x. So any such vector x is called an eigenvector corresponding to the eigenvalue lambda. Right? And the set of all eigenvalues of a given matrix is called the spectrum of the matrix. And how do you find or how do you compute the eigenvalues of a matrix? You basically solve for the characteristic equation. Take determinant of A minus lambda times I, find all solutions. So this determinant is essentially going to be a polynomial of degree n. You find all of the n roots of this particular polynomial, and the roots are going to be the eigenvalues of the matrix A. Okay. And how do you find the eigenvectors? So you need to find the set of all vectors that satisfy Ax equal to lambda x. Maybe lambda, you've already found the eigenvalues of this particular matrix by solving the characteristic equation. And so for each lambda, you try to solve for Ax equal to lambda times x, or effectively A minus lambda I times x equal to 0. Again, all you need to do is do row reduction, right, to find the solutions. So once again, the computational complexity of finding the eigenvalues and eigenvectors is only as much as the computational complexity of doing row reduction. Right? So that's the nice feature about these basic things in linear algebra. All of these problems, finding the determinant, finding eigenvalues, finding eigenvectors, solving a system of linear equations, finding the inverse of a matrix, all of these can just be performed using row reduction. The computational complexity is just as much as finding the row reduced echelon form of a matrix. If you can find the row reduced echelon form, then you can do all of these. Right? So that's the beauty of linear algebra. Yeah.
Do you have to do that RRAS for each of these systems?
You will have to, but
It will n to the 4th.
that is correct. Yeah. So you have an additional factor of n, again depending on what is the multiplicity of each of the eigenvalues, but in the worst case, that's right. So it will be n times the complexity of finding the row reduced echelon form. So instead of order n cube, the computational complexity is going to be order n to the 4. That's right. Right? Any questions? Okay. So these are sort of analytical descriptions of the eigenvalues and eigenvectors of a matrix, but let's see some geometric or physical interpretations of the determinant as well as the eigenvalue and eigenvectors. All right. So what we can do is we can think of how the matrix A operates on certain sets or certain subsets of Rn. Right. So what is A? A is a matrix which can be viewed as a linear transformation from Rn to Rn. It's an n by n matrix. Right. So it's a linear transformation, and you can see what happens to sets when you sort of deform it using these linear transformations. So you have some set in Rn, maybe you have a cube, you can transform it using this linear transformation that is defined by the matrix A, and then you can see what happens to this. You get some other set. Right? So let's see what happens. So you take this particular cube, I'll define the n-dimensional unit cube as the set of all vectors x such that each xi is between 0 and 1. So in 2 dimensions, it is just this cube plus 1, 1. Right? So it's this region over here. Right? Now this is, you can define this region using just in 2 dimensions. You can just define it using the vertices. Right? If you know what happens to the vertices or how the vertices get transformed by the matrix A, then effectively, if all points in between are going to sort of lie within what is defined by the vertices. Right? So let's look at these vertices. What do these vertices get mapped to? So let's look at the following set, which is the set of all A times x, for which xi is between 0 and 1. you know that if I leave out this particular A, it just gives me this cube, correct? And I can define the cube using its vertices, right? Now let's look at just two of these vertices, this vertex and this vertex. If I look at the transformation, what would be the transformation of this particular vertex in terms of the matrix A? A, yeah, correct, it is A times this vector, but what is it exactly? It's just the first column of A, right? Because what vector is this? Is just the standard basis vector, right? So this vertex just gets mapped to the first column of A. This vertex gets mapped to the second column of A, and so on in n dimensions. That is all that happens. So this cube, some of the vertices are basically the standard basis vectors for Rn, right? The other vertices are just integer linear combinations, or basically sums of vertices, sums of these standard basis vectors. But what do the standard basis vectors get mapped to when you multiply by A? It's just the corresponding columns. So effectively what happens is that if you transform a cube by a linear operator A, then it gives you a polyhedron. So basically in 2 dimensions, the cube or the square gets mapped to a polygon, nothing else, right? And this polyhedron, what are the vertices of the polyhedron? Some of the vertices are just going to be the columns of the matrix A. The other vertices are just going to be sums of columns, nothing more, right? So you can in fact try to just visualize it using a simple example. Let's just take this matrix. So it will be a running example for us. It's a symmetric matrix with entries 1, 0.3, 0.3 and 1. All right. So let's start with this. It's just a simple program where I plot it's a bit slow. Yeah. So it's just the cube, nothing else, right? I've just plotted a bunch of points which lie within the square. So this blue region is just this, the unit cube. Now what I'll do is I'll multiply each point within this cube by A, right? And visualize what set I get. I just get this. It's in fact, because the matrix is symmetric, I'll get a parallelogram, and as it turns out, this particular vertex is going to be, so this particular vertex is 1.2. This particular vertex is also, I think, yeah, 1.2 comma 0.3. I used a different matrix there. Let me just follow the same thing. It'll be slightly easier to visualize with this. So this point is just 1 comma 0.3, and this vertex is 1 comma 0.3 comma 1, and this vertex, so this is basically the first column, this is the second column, and this vertex is just going to be a straight up sum of the two columns of A. It's just 1.3 comma 1.3. Right? So that is what happens. So the matrix A defines the vertices of this parallelogram, or in general this polygon. And one interpretation of this linear, one physical way of interpreting a linear or matrix multiplication is that it transforms the cube into a polyhedron which is defined by the columns of A. Right? That's one interpretation. But what is nice, what is very interesting is, now what is the volume of this particular cube? It's an n-dimensional cube. Each side has length 1. So what is the volume of the cube? It's equal to 1. And it turns out that the volume of this particular polyhedron is going to be exactly equal to the determinant of A. Right? I will not prove this, but it's not too difficult to do it. It's just you represent the volume of a region by an integral, and you'll see that the linear transformation essentially corresponds to, if you do a change of variables, it's as good as multiplying by the absolute value of the determinant. All right, so that's one interpretation of the determinant. You take a cube, you transform it by A, you'll get a polyhedron, and the volume of this polyhedron will exactly be equal to the determinant of A. Right? Now let's look at another set. Right? So that's transformations of the cube. Let me try to see what happens if I take a circle or a sphere and again do the same thing. I take the sphere, which is a set of all vectors whose L2 norm is less than or equal to 1, and then multiply each vector in this set by A. I'll get a new set. And this new set is basically going to look like an ellipse. In 2 dimensions, it will be an ellipse. In higher dimensions, it's going to be an ellipsoid. Right? And so let me just see what happens. So for the same matrix, so first I've just generated a bunch of random points, all lying within a circle of radius 1. Right? Don't worry about how I did this or anything. It's not particularly important or even relevant. Now, for each one of these random points, I'll just transform it and see what it looks like. All right. So the vector y is just a transformation of all of these points. So it looks just like an ellipse. Right? It is basically an ellipse, and maybe it's not clearly visible, but it's going to be an ellipse. But what is important for us are, what are the major and minor axes going to be, right? That's what is particularly, because that is what completely defines the ellipse. If you know what the major and minor axes are, then that tells you then that completely describes the ellipse. So the major and minor axis, you can think of it in terms of these points: this point over here, this point over here, this point over here, and this point over here. Right? I'm not sure if you can all see this clearly. Right? So let's see what this point here is. You can, in fact, if I'm not sure if the font size is big enough, but this point happens to be close to whatever 0.9 comma 0.9, right? Yeah, whatever 0.917, 0.917, and this point over here happens to be whatever, roughly 0.487 minus 0.49 something, right? And you can also try to find out what is the length of each of these vectors. In fact, let me do the following. Save this. right? So I took the sphere and I took the circle, I just transformed by this matrix, right? And what I'm interested in right now are these points, this point over here and this point over here, right? So these two vectors, maybe I'll use a different color, this vector and this vector. This vector and this particular vector, right? As it turns out, these two vectors are basically going to be the eigenvectors of the matrix, and the length of these vectors are going to be the eigenvalues, the corresponding eigenvalues. Okay? So if for this matrix, if you try to find the eigenvalues and eigenvectors, it has two eigenvalues, 1.3 and 0.7, and the corresponding eigenvectors are 1 by root 2, 1 by root 2, and the other is going to be 1 by root 2 minus 1 by root 2. In fact, this vector is just going to be this times 1.3, and this vector is just going to be 0.7 times this particular vector. Okay. So that's another geometric interpretation of the eigenvalues. So if you take a sphere, the unit sphere, and transform it using A, then basically you get an ellipsoid where the major axis, the basically the principal axis have lengths equal to twice the each of the eigenvalues. So the length of this is basically going to be 2 times 0.7. This length is just going to be 2 times 1.3. Right? So the principal axes are completely determined in terms of the eigenvalues and the eigenvectors. So they define the principal axis of this ellipsoid. Right? And one intuitive way of thinking why that is true is the following. So if you think about a sphere, right? You take the unit sphere, correct? Now this unit sphere has all points. If you take the surface of the sphere, then it contains points whose norm is exactly equal to 1, right? Or you take any sphere for that matter. Now if you take an eigenvector which lies somewhere on this particular sphere and you multiply it by A, what happens? The eigenvector just gets scaled, right? Any other vector would get maybe scaled and maybe rotated, but these eigenvectors are only going to get scaled. And by how much are they going to get scaled? They're going to be get the amount of the scaling is exactly going to be equal to the corresponding eigenvalue, and that is really what is happening. That's one way of interpreting what happens to the unit sphere, right? So this is, of course, I'm assuming that it's a full rank matrix, right? If it's not full rank, then I have an n-dimensional sphere. If I try to multiply it with the matrix A, then I don't end up with an n-dimensional object. So for example, if I take the circle and then I multiply, but I can do it right here. So I had this original transformation, right, where I was multiplying by the matrix 1.3.31. Instead, let's say that I just multiply by 1.3, close this. So I have 1.3, 1, 0.3 at the original circle. I'm transforming this, I just end up with a straight line. So it's not a full n dimensional object. It just collapses down to a smaller dimension. It's going to be an ellipsoid, but it's going to be an ellipsoid in a smaller dimensional space. Right? Okay. So that's about what happens to the ellipsoid. The other nice property is that the volume of this ellipsoid is basically going to be the volume of the unit ball in n dimensions times the determinant of A. And again, you basically get this determinant by a change of variable, nothing else. Right? So Bn is the volume of the unit ball in n dimensions. So in 2 dimensions, this is just pi. In 3 dimensions, this is going to be 4 by 3 pi. In n dimensions, this is just going to be equal to, in fact, pi raised to n by 2 divided by gamma n by 2 plus 1, where gamma is the gamma function. All right. So that's sort of the geometric interpretation of what happens when you apply linear transformations. Right. So basically, you take a set which has a certain volume, and then you multiply all of these points by A, you'll get a new set, and effectively all that happens is that the new set has volume equal to the volume of the original set times the determinant of A. So that's one way of thinking about the determinant of a matrix. In fact, for let's say R2, you can try to explicitly find out. You can try to find out the area of a region using the integral, and then if you transform it by A, you can see that if you again do change of variables and try to find the volume of the area, you just get this factor determinant of A as multiplying this. Right? Okay, so now we know. So suppose I give you a particular matrix. How do you compute the eigenvalues? You solve this polynomial. You find the roots of the characteristic polynomial. And how do you find the eigenvectors? You just solve a system of linear equations. Right? But let's go back. There's something that I didn't explore, which is, if I give you an arbitrary n by n matrix A, is it guaranteed to have n real eigenvalues? Yes? No? No. Why? What can happen? Some of the eigenvalues can be complex. Basically, what you have is a polynomial in n variables, and you want to see what are the roots of this polynomial. Not every polynomial in n roots has n real roots. Right? So polynomial of degree n may not have n roots. Right? And can you give me a simple example of a matrix which does not have n real eigenvalues? Yeah? 0, -1, 1, 0. Are you sure this does not have? I think you meant 0, 1, 1, 0. Right? So what will be the characteristic polynomial for this? So this is just whatever lambda square plus. Okay, I think it's that was correct. Good. Okay, this is lambda square plus 1, and the roots of this particular polynomial are plus or minus I. Okay. So this does not have real eigenvalues. But does every n by n matrix A have n complex eigenvalues? Eigenvalues? Yes, it does have n complex, right? But what is more important for us, suppose I have a matrix, so irrespective of whether the eigenvalues are real or complex, even over the space of complex numbers or complex vectors, does every n by n matrix A have n linearly independent eigenvectors? No, right? Can you give me an example? Yeah, 1 1 1 1 1 1 1 1.
Singular matrix.
Why?
Sorry, any singular matrix.
Why any singular matrix?
So the multiplicity of the zero eigenvalue is the rank of the null space.
Does this have n linearly independent eigenvectors? What are the eigenvalues of this matrix? 1 and 0, right? So this has eigenvalues 1 comma 0, and can you find one eigenvector for 1? You just take the vectors 1 0. What is this vector times this matrix? It's equal to 1 0. What if I take this vector times this matrix? I get 0 0, which is equal to 0 times 0 1. Right? So these two are in fact linearly independent eigenvectors for this matrix. Right? Depends on. Okay, so does it mean that if eigenvalues are repeated, then the matrix, then you cannot find n linearly independent eigenvectors? Correct. So firstly, in general, not every n by n matrix can have n linearly independent eigenvectors, right? So one example is this particular matrix. All right. I leave it as an exercise. Try to convince yourself, and it's easy to try to see why. So you just multiply by x1, x2. If this has to have an eigen, so firstly you can try to find the eigenvalues of this matrix, and then try to see if there is any non-zero vector such that this is equal to lambda times x1, x2, if it is possible to ever have this, okay, for both the eigenvalues, or is it possible to have n linearly independent, two linearly independent vectors x1 of the form x1, x2 which satisfy this. Okay, so that's an exercise. So the answer to this question is no, not every n by n matrix A can have n linearly independent eigenvectors. Okay. And one thing to note is that even if some of the eigenvalues are repeated, you could still potentially have n linearly independent eigenvectors. And essentially the main result is the following, that if you have n linearly independent eigenvectors, so in other words, the eigenvectors of A form a basis for Rn, then the matrix A is diagonalizable, which means that I can write the matrix A as some matrix P times a diagonal matrix D times P inverse, where P is non-singular, of course. So A is diagonalizable if and only if the eigenvectors of A form a basis for Rn. Or in other words, I can find n linearly independent eigenvectors. I could have more than one linearly independent eigenvector corresponding to the same eigenvalue. That's one thing to always keep in mind. So, for example, if I just take the identity matrix, it just has one eigenvalue which is repeated n times. And if I take any n linearly independent vectors, these all form eigenvectors of the identity matrix. Right? So, but so whether an eigenvalue is repeated or not doesn't determine whether the matrix is diagonalizable or not. However, if none of the eigenvalues are repeated, if all of the eigenvalues are distinct, then A is diagonalizable, right? But there's a small thing that you need to be careful about, which is that the eigenvalues must be distinct and real, right? Because after all we are looking at when we talk about diagonalizability and eigenvalues and eigenvectors, in this particular course, we're only dealing with Rn. So we want our eigenvectors to be real. We want all the eigenvalues to be real, okay? Which is not guaranteed for general matrices. But there's a special class of matrices for which all of this becomes easy. We don't have to worry about this too much. And that is the set of n by n symmetric matrices. So throughout the set of symmetric matrices will come up very, very often. And I'll denote the set of symmetric matrices as S, sometimes as Sn. If it is not clear whether it's n by n symmetric matrices or not. Right? So in general, S is going to be the set of all n by n symmetric matrices. And as we've seen previously in an earlier class, the set of all symmetric matrices forms a vector space, and the dimension of this vector space is n into n plus 1 by 2. Right? Correct. So basically, a matrix A is diagonalizable if and only if for each eigenvalue lambda, the arithmetic multiplicity of lambda, which is basically the number of times lambda is a repeated root of the characteristic polynomial, should be equal to the geometric multiplicity of lambda, which is basically, if you look at A minus lambda I equal to 0, what is the space of solutions? Or in other words, what is the dimension of the null space of A minus lambda I? Right, so it all boils down to just this. Great. Okay, so now let's go back to so now we are going to explore a special subclass of matrices, which is the set of all symmetric matrices, n by n symmetric matrices. The nice property about symmetric matrices is that symmetric matrices always have real eigenvalues. All of the eigenvalues are guaranteed to be real. They're guaranteed to be diagonalizable, and more importantly, they're guaranteed to be orthogonally diagonalizable. So I can find a set of n orthonormal eigenvectors which span Rn. Right? So I can form an orthonormal basis purely using the eigenvectors of A. Right? I won't prove this completely, but we can see some things as to why. So I will not prove that A is diagonalizable and the eigenvalues are real, but let's see why the eigenvectors should be orthogonal, or why we can choose the eigenvectors to be orthogonal to each other. Okay, that's fairly easy to see. So let's take any two eigenvalues. Let's take lambda 1 and lambda 2, which are distinct. So lambda 1 is not equal to lambda 2. Okay, and let us say that v1 is an eigenvector corresponding to lambda 1 and v2 is an eigenvector corresponding to lambda 2. Now if v1 and v2 are orthogonal to each other, then it must mean that the dot product of v1 and v2 should be equal to 0. So let's do the following. Let's take v1 transpose a times v2. Okay, I'll just look at this quantity. v1 transpose a v2. What is this equal to? This is equal to, what is a times v2? It is lambda 2 times v2. So this is v1 transpose lambda 2 v2, which is nothing but lambda 2 times v1 transpose v2. So it is lambda 2 times the inner product between v1 and v2. Okay. Now let me compute v2 transpose a v1. Right. This is the same as if I take the transpose of this. What do I get? I just get v, or let me do it the other way around. Let me start with this for convenience. v1 transpose a transpose. Let me do it that way. Let's look at v2 transpose a times v1. Right? What is a times v1? Or in other words, I could also take the transpose of this whole thing, right? Which is just going to give me v2 transpose a transpose times v1, which is just v2 transpose. So these two remember that these two quantities are equal to each other because this is just a real number. So the transpose is equal to the number itself. So this is v2 transpose a times v1 because a transpose is equal to a. Remember, these two are equal to each other. But this is equal to, what is a times v1? It is lambda 1 v1. So this is just lambda 1 times v2 transpose v1, which is the same as lambda 1 times v1 transpose v2, because v2 transpose v1 is equal to v1 transpose v2. Right? They're both the inner product between v1 and v2. We're dealing with real matrices, real vectors. So this means that lambda 2 v1 transpose v2 is equal to lambda 1 times v1 transpose v2. And lambda 1 is not equal to lambda 2. When can that happen? That can happen only if v1 transpose v2 is equal to 0. So v1 transpose v2 should be equal to 0. Right? So again, the only property that we've used is that if you look at v1 transpose a v2, this is equal to this thing transpose, which is just v2 transpose a transpose v1, right? But a transpose is equal to a since a is symmetric. This is not true. So going from this step to this step is only true because a is symmetric. If it were not symmetric, then the rest of it would not follow. But this is nothing but lambda 2 times v1 transpose v2, and this is nothing but lambda 1 times v1 transpose v2. And since lambda 2 is not equal to lambda 1, that can only happen if v1 transpose v2 is equal to 0. So if you take any two eigenvectors corresponding to distinct eigenvalues, no matter how you choose these eigenvectors, as long as they correspond to distinct eigenvalues, they're going to be orthogonal to each other, right? Now, okay, so now I can construct orthogonal eigenvectors, but what about eigenvectors corresponding to the same eigenvalue, repeated eigenvalues? I know that, again, you have to believe me when I say that any symmetric matrix is diagonalizable, okay? Which means that the geometric multiplicity is equal to the arithmetic multiplicity, even if the eigenvalue is repeated. Right? So if the eigenvalue is repeated, if some lambda is repeated, then the eigenspace right, which is the set of all vectors, set of all eigenvalues, eigenvectors corresponding to the eigenvalue lambda, then the eigenspace which corresponds to lambda has dimension equal to the arithmetic multiplicity of lambda. Correct? Now in this eigenspace, what can I do? I can find any set of linearly independent or any basis for the arithmetic multiplicity, any basis for the eigenspace, but in particular I can also find an orthogonal basis for the eigenspace. So here I can choose, so basically I can choose orthogonal vectors, right? Orthogonal basis for this particular eigenspace. So I have an eigenbasis for this particular eigenspace, right? These are all orthogonal to each other, and I have the eigenbasis for another eigenspace. Again, they're all orthogonal to each other. But then if you take any vector from here and any vector from here, I'm guaranteed that they're going to be orthogonal to each other because of this particular property. So I put them all together, I just get an orthogonal basis. Right? So that's the speciality of symmetric matrices. I can construct an orthogonal basis. But I'm sorry?
Eigenspace dimension.
The dimension is equal to the geometric multiplicity, which is equal to the arithmetic multiplicity. Again, I have not proved it, but the claim is that the arithmetic multiplicity is always equal to the geometric multiplicity, and all of the eigenvalues are real. I'm just using this as a fact. All right. But more interestingly, so recall that if a matrix is diagonalizable, then A can be written as P D P inverse, right? But what exactly is P, or what are the columns of P correspond to? The eigenvectors, right? And now I can construct an orthonormal basis, correct? So what is P inverse going to be equal to? It is just going to be equal to P transpose. So for a symmetric matrix A, this is equal to P D P transpose. All right. So a symmetric matrix is orthogonally diagonalizable, but the reverse is also true. If a matrix is orthogonally diagonalizable, then it must be symmetric. All right. So if A is orthogonally diagonalizable, then A must be symmetric, and this is easier to see. So If it is orthogonally diagonalizable, then it means that I can choose a basis of eigenvectors which are orthonormal, correct? Then what is P inverse equal to? It's equal to P transpose. So this is equal to P d P transpose. But what is A transpose equal to in this case? Here I'm only assuming that A is orthogonally diagonalizable, which means that P transpose is equal to P inverse. Which means that P transpose is equal to P inverse. I can construct a P such that P transpose is equal to P inverse. What is A transpose equal to? It's P d P transpose whole transpose, which is nothing but P d transpose P transpose, but D is a diagonal matrix, so this is just P d P transpose, which is A. Right? So that's a useful property to know, that an n by n matrix is symmetric if and only if it is orthogonally diagonalizable. Right? Great. So among the class of symmetric matrices, where we can restrict ourselves even further. So in particular, if I look, so now we essentially come down to restrictions, right? So initially I looked at arbitrary n by n matrices. The eigenvalues could be real or complex. It could be diagonalizable, it need not be diagonalizable. Now if I restrict myself to symmetric matrices, then I'm guaranteed that it is diagonalizable, it is orthogonally diagonalizable, and the eigenvalues are real, but the eigenvalues could be positive or negative. Now let me impose another restriction saying that I want all of the eigenvalues to be non-negative. Right? Then I get this, basically get this set of positive semi-definite matrices. So for now I'm going to define the set of positive semi-definite matrices, or I'm going to define a positive semi-definite matrix, or PSD for short, if it's symmetric and all of the eigenvalues are greater than or equal to 0. All right? And I'll say that it is positive definite, or PD for short, if all of the eigenvalues are strictly greater than 0, positive. Okay?
Why didn't you go the other way around? I mean, plain seems more intuitive for the definition of PSD than
Whatever. Again, it depends. So there are, in certain places you define this as the set of positive semi-definite matrices. Sometimes you just use this, but in any case they're both equivalent, which is what I want to, that's the point I want to make next, that matrix is PSD if and only if x transpose AX is greater than or equal to 0 for all vectors x. All right. It's not too hard to show this. Effectively, it's simple. So if A is, so we know that A is symmetric, firstly, right? And A is PSD. So from A, I can construct a basis, an orthonormal basis of eigenvectors. Of eigenvectors. All right. Let me say that the eigenvectors are v1, v2 up to vn. All right. So each vector has a norm exactly equal to 1, and vi transpose vj is equal to 0 for all I not equal to j. Right. So I know that vi transpose vj, this is equal to 1 if I equal to j, and it's equal to 0 if I is not equal to j. And let me say that the corresponding eigenvalues are lambda 1, lambda 2 up to lambda n. These are real because I know that it's a symmetric matrix, so n real eigenvalues exist. Lambda 1 through lambda n need not be distinct. They could be repeated, but I don't care. Some lambda 1 through lambda n. And since if it is PSD, I know that all of the lambda i's are going to be greater than or equal to 0. Greater than or equal to 0 because this is a PSD matrix. by definition. Now remember that V1 through Vn forms a basis for Rn, which means that if I take any vector x, doesn't matter which vector it is, I can write it as a linear combination of the basis vectors, the eigenvectors. So I can write it as I equal to 1 to n of some alpha I vi, right? So if I take x transpose Ax, this is nothing but x transpose A. Now x is equal to this particular quantity, summation I equal to 1 to n alpha I vi. Let me just write that down. I equal to 1 to n alpha I vi, which is nothing but x transpose. Let me take the matrix inside the summation. So I get summation I equal to 1 to n alpha I times avi, right? But what is avi equal to? X transpose. So this is summation I equal to 1 to n alpha I. Avi is nothing but lambda I vi, since vi is an eigenvector. Right? Okay. Now let me also write down x as summation I equal to 1 to n alpha I vi. What I get is summation, let me say j equal to 1 to n alpha j vj transpose summation I equal to 1 to n alpha I lambda I vi, which is nothing but summation j equal to 1 to n alpha j alpha I lambda I vj transpose vi. Right? I'm done nothing else, just manipulation. But now, so I'm sorry, there should be a summation I over I also. Right? But what is Vj transpose Vi? Remember, they're orthonormal eigenvectors. So Vj transpose Vi is equal to 0 if j is not equal to I, and it's equal to 1 if j is equal to I. So this is nothing but summation I equal to 1 to n alpha I times alpha I, which is alpha I squared, times lambda I times Vi transpose Vi, which is 1. What can you say about this? This is non-negative because the lambda i's are all greater than or equal to 0. Alpha I square obviously has to be greater than or equal to 0. So this quantity is greater than or equal to 0. Which means that if x is positive semi-definite, then x transpose Ax is greater than or equal to 0 for all vectors x. Right? And again, if it is positive definite, then all of the lambda I should be strictly greater than 0, and the alpha, at least one of the alpha i's should be non-zero, because we're looking at non-zero vectors x. So then this quantity would be strictly greater than 0 for every non-zero vector x. Zero. All right. So that's a useful, and you can also prove the other way around. that if you take a symmetric matrix X and this is greater than or equal to 0 for all X, then the matrix must be positive semi-definite. It's in fact easier to do than this, but I leave it as a homework. All right. Okay. So I'll just begin with, I'll conclude with some points which I won't prove. Maybe we'll see this at a later point during the course. But the set of all positive semi-definite matrices forms a closed set. Right? That's something useful to keep in mind. And the set of all positive definite matrices, which I'll denote S plus plus. So S plus will mean the set of all n by n symmetric positive semi-definite matrices, and S plus plus will be the set of all n by n positive definite matrices. So this forms an open set, whereas this will form a closed set. In future we'll keep sort of revisiting this positive semi-definite and positive definite matrices. Another nice property about a positive semi-definite matrix is, just as every non-negative number has a square root, every positive semi-definite matrix also has a square root. You can define, so if I have a matrix A, I can write this as P D P transpose, orthogonally diagonalizable, and every entry of D is non-negative. So if I look at P D to the power half, so all of I take the square root of all of the diagonal entries times P transpose. Let me call this some A prime. Then if I multiply A prime with itself, P transpose, I have P transpose P, which is the identity matrix, D to the power half times D to the power half, which is D. So this is just P D P transpose. Right? Okay. So I'll stop here. So with this, we've sort of covered whatever we needed for in terms of linear algebra and calculus. And from next class onwards, we'll begin with convex analysis. Right? Convex sets, convex functions, and how do you do unconstrained convex optimization.